Hi guys, welcome to today's lesson. This is tests for independence. So in probability, two events can be independent, meaning like you roll a die and you flip a coin and the outcome of the die roll has no effect as the outcome of the coin flip. So when you flip a coin, it's always 50-50. It doesn't matter whether or not you rolled a 1 or a 2 or a 3 on a die. Those are independent events. Then there are dependent events where one depends on the other. So for example, if you are a nurse, that may make the probability of you getting COVID-19 more likely. So those events would be dependent. What's kind of cool in just the mathematics of it is you don't even need to know what the events are. All you need to know are the probabilities of those events happening, and you can determine whether or not the original events were dependent or independent. So again, we don't even need to know what the events were. It could be spinning a wheel. It could be the probability of getting hit by lightning. We don't need to know what those are. We can just actually backtrack and reverse engineer from the probabilities themselves and determine what types of events those are. We're not going to be able to say, oh, based on the probability being 0.57, that has to do with a lightning strike. It's more of just we would be able to say whether or not two events are dependent or independent. I'll get going with an example. So this is test for independence 1. There are 2 of them. And this formula should look familiar, okay? If this formula holds true, then the events A and B are independent, okay? And this goes both ways. If A and B are independent, then the formula holds true. So A, B, independent. That means that the formula is true. But also, if the formula holds, that means that A and B are independent. So this is a really strong, I guess, test. So we've got here PA equals 2, P of B equals 0.1, P of A and B equals 0.3. Are A and B independent? We don't know what A is, but that doesn't matter. So we have probability of A and B equals probability of A times probability of B. I'll substitute in probability of A and B is 0.3. Probability of A is 0.2. Probability of B is 0.1. So if this equation here holds, then A and B are independent events. What events those are, I don't know, but they would be independent. So I'm going to do 0.2 times 0.1 equals 0.02. So 0.3 does not equal 0.02. Hence, the events A and B were not independent. So that means event A could not have been a coin toss, and event B could not have been a die roll, for example. Right? We don't know what A and B are. We just know that they are not independent events, and not independent events. Another way of saying that is that they are dependent events. Okay, so this is test 1, which we've seen before. This is test 2, and I kind of showed this. I'll do an example first. Probability of A. So if you have A given B, okay, if this matches this, then they are independent. So if the first one matches the second thing, so this is the second test for independence with givens. So here they say if probability of A equals 0.4, probability of A given B is 0.4, are A and B independent? Well, we would write our test for independence as the probability of A given B. Does that equal the probability of A? If so, A and B are independent. Well, A and B, probability of A given B, A given B is 0.4. Does 0.4 equal the probability of A? 0.4. Yep. so the events are independent. And I had shown the mathematical reasoning behind that. So let me just show you where this formula comes from. Assume A and B are independent. That means that this implies the probability of A and B equals the probability of A times the probability of B. Okay, so keep that in mind. Now, we'll write out the given formula. Try it in green. The probability of A given B is equal to the probability of A and B over the probability of B, right? These. Well, if they're independent, this holds. So that means we can rewrite the numerator as probability of A times the probability of B, whereas the denominator stays the same. And now a probability is a number, so these numbers would divide to 1, and this would be the probability of A. And if I rewrite this, the probability of A given B, if A and B are independent, simply equals the probability of A. So that's the second formula, that's where it comes from. I'm going to do just 2 examples, actually 2, yeah. Okay, use the data below and both tests, okay, to show whether or not the events are dependent or independent. So let's see. So when it comes to this type of table, let's see, we're going to do the probability of male, how about, and passing. Does that equal the probability of being a male times the probability of passing? Passing. Now you may be wondering, well, why did you choose probability of male and passing? It actually doesn't matter which I choose. I could have chosen the probability of male and passing. I could have chosen the probability of male and failing. I could have tested the probability of female and passing, or I could have tested the probability of female and failing. And if you think about it a little bit, if male and passing, if these are independent, that kind of means that all these other ones have to be independent. It's subtle, don't overthink it, but if you want a little practice, think about that. So the probability of being a male and passing is 54 over 210. The probability of just being a male in this situation is 84 over 210. And the probability of just somebody that passed is 135 over 210. So let's do this. 84 times 135. This is 11,340. And 210 times 210 is 44,100. So we want to see, do these fractions equal one another? 54 divided by 210 is equal to 0.257 about. And we want to know, does that equal 11340 divided by 44100 using a calculator? Believe it or not, they equal the same thing. Okay, so this means that it doesn't matter for this test whether or not you are a male or a female, that doesn't make a difference on the outcome of the results of this test. I don't know what the test would be. I have no idea what type of test would weigh one would, it could be anything. I know that there are some tests that females are better at. For example, females have better vision than men in general. They can see closer to the ultraviolet. So I know that this isn't an eye test. It could just be an SAT test or something like that. And let's use the other test. The other test is basically, let's choose the probability of female given failing. Does that equal the probability of just being a female? So the probability of female, given that you failed, is 45 over 75. Does that equal the probability of just being a female in this study, 126 over 210? I'm going to use my calculator. Should be correct, independent. So the left-hand side is 0.6. And the right-hand side is 0.6. Okay, so using either test, and actually you could see that the second test is much faster. It shows that whatever test it was that these male and females took, their gender had no role in determining whether or not they passed or failed the test. I'm gonna do this practice one really quick, just because it's a little different. Given events A and B. You know what? I need to make a little room. Just follow me through this one. This is a classic question. So I see that I have this formula here. So don't forget about this one. The probability of A or B equals the probability of A plus the probability of B. Right, that's a plus, minus the probability of A and B. You might be thinking, what the heck are we doing with this OR formula? Well, let's read through the problem. Given events A and B such that the probability of A equals 0.6, the probability of B equals 0.5, probability of A or B equals 0.8, determine whether A and B are independent. Well, in order you use that test for independence, we need to have the probability of A and B. Does that equal the probability of A times the probability of B? We have this, we have this, we don't know this, but we can solve for that using this other formula. So let's go back. 0.6 plus 0.5 is 0.11. Okay, minus probability of A and B. 0.8 minus 0.11. So we done minus 0.11 on both sides. 0.8. Sorry, this should be 1.1. Negative 0.3 equals negative probability of A and B. Just multiply both sides by -1, and you get the probability of A and B equals 0.3. So you had to do a little work, but now we have all three components. We substitute them in to do the test. Does 0.3 equal 0.6 times 0.5? Well, what do you guys think? Yes, 0.6 times 0.5 is 0.3. And our conclusion is that A and B are independent. Okay. So this is like a pretty classic problem where you're asked for whether they're dependent or independent, but you don't have enough information and you need to use this formula to kind of figure that out. Okay. This was only about a 15-minute video. Attempt the delta math. We'll meet at 1 p.m. on Thursday to go over it, and email me if you guys have any questions. If you're super stuck, just look through the examples on delta math and look back through this webinar. But I want you to attempt the problems before you email me, because I think that you'll find with a little effort you can figure this stuff out. Okay, enjoy your days, and Friday I don't think we'll really be doing anything. Okay, have a good one.